Welcome to the Connecticut Center for Advanced Technology, the state and region's technology provider. My name is Ron Angelo, and I'm the President and Chief Executive Officer of this phenomenal institution. In a moment, you will hear from CCAT's experienced team of engineers and technology experts. We are at the center of CCAT's Manufacturing Innovation Hub, where innovative companies and startups gather to develop their companies and launch their technology. CCAT's mission is to validate, demonstrate, and assist companies in adopting leading-edge technologies. Now let's go meet the team that makes that happen.
My name is Jeff Crandall, and I'm the Additive Technologies Manager here at CCAT. So my job is to introduce companies to additive technologies. 3D printing, additive manufacturing are all names for the same thing. Additive is one of the new Industry 4.0 technologies that's beginning to take over manufacturing. And so additive is becoming a very important tool. It's emerging from primarily rapid prototyping tool or a laboratory tool into mainstream manufacturing. When you look at additive compared to conventional manufacturing processes, there's a lot of positive attributes. So one of those is there tends to be much less waste. So here again, early adopters in the aerospace industry are reporting as much as a 90% reduction in material cost as a result of using additive manufacturing, because the material, you add it where you need it, and you can reuse the powders in particular that we use, so there's very little waste in the process. You can design a part that has the same function as a traditionally manufactured part, the same strength, the same attachment points, but you can manufacture that considerably lighter. So a lot of times that involves these interesting organic shapes. These are very difficult to manufacture using conventional technologies, but it's very simple to manufacture using additive technologies. So here again, when you look at lightweighting, one of the early adopters is Airbus. They think that by using additive technologies, they can reduce the weight of an airplane by as much as 2,000 pounds. So when you look at the annual fuel savings for that multiplied by the life of the airplane, you look at the fuel savings from that multiplied by the number of airplanes in a conventional fleet, and you look at the amount of carbon that's not going into the atmosphere from a green perspective, that's huge. And those are reasons why the industry is excited about it. It's hundreds of millions of dollars a year in fuel savings and hundreds of millions of tons of carbon that's not going in the air. So it's very, very substantial. Other reasons that people are looking at additive manufacturing is for the concept of part consolidation. So it's very relatively simple to make very complex parts that are difficult to do or impossible to do using conventional technologies. And so by making more complex parts, you can actually consolidate a number of parts in a single build. And with that idea in mind, some people are reporting as much as a 95% inventory reduction as a result of it. So that's less suppliers that you have to manage, less product that you have to warehouse and logistically support. As additive starts to take an inroad as a mainstream manufacturing tool, a lot of the large companies are starting to vet their supplier base into those that have additive as a tool and those that don't. And a lot of those large companies are predicting that in the next few years, they're going to see a shift in their supplier base to those that have additive as a tool. So it's important, if a company waits until they receive their first request for quote for an additively manufactured part before they get involved with it, it's too late. So it's pretty much a 2-year window. So there's a lot of people around the United States and around the world that have already begun their journey as additive manufacturers. Injection molding, machining, turning, grinding. There's a number of different families of technologies that we use today for traditional machining processes. When you look at additive manufacturing, there's also a family of technologies. So by definition, there are 7 different technologies, 8 if you include hybrid manufacturing, which we have. Right now, CCAT has 3 of the 7 different technologies. So we're in the process of expanding the technology offerings that we have so that any manufacturer can come to us no matter what their product that they're building, and we'll be able to look at whether or not it makes sense for them to explore using additive as a tool, and then validate which technologies are going to make sense for them. When you look at the people that are actively adopting additive today, the space industry is one of those. And so there's a lot of things that we're exploring on new frontiers as far as multiple materials and going from conventional materials that aren't weldable together but you can use in an additive process. So there's a lot of things that you can do with it. We're exploring different additive processes that we can add material back, remachine it, and now you have a part that's as good or actually in some cases better depending on what we use to build back the material. So the idea of legacy parts that can be built on demand when you need them eliminates the whole concept of having warehouses filled with parts for year after year. So when we look at additive technology, there's really no bounds or end to the industries that can take advantage of it. So when you look at some of the new technologies coming up, fuel cells and wind power, there are applications. So, and it might be using a robotic, polymer system to build a mold that then you're going to cast a composite with, or it could be building something like this, which is a reactor for converting carbon dioxide to other chemicals. It has very small 1 millimeter tubes that run all the way through it. They're coated with a catalyst, but this is built as a single part. So there's no way that you could build this part using other conventional processes. People have been casting and welding and making metal parts for somewhere around 5,000 years. And people have been doing work in additive for the last 20 years. And so there's a comfort level with what the traditional processes are and what the product of that is. People understand that very, very well. One of the concerns with additive is it as good as a conventionally made part? And the answer is probably yes, possibly better. And there's a tremendous amount of research that's being done in the industry and in the individual companies. So when you look at a lot of what I call the early adopters that are still beginning to move into this in a big way, so medical, aerospace in particular, the Department of Defense, there's an immense amount of money being spent on research to make sure that the material characteristics and the material qualities are as good or better than what are made conventionally.
My name is Christy Oki. I am a manufacturing applications engineer. My background is in mechanical engineering, and I help to support our manufacturing technologies and help companies learn about new Industry 4.0 technologies and adapt them into their workflow. So some of our focus areas include automation, so rather than having things that might have previously been done by hand or done by people, having those be done by robotics and other automated systems. We also focus on additive manufacturing as well, so making parts rather than subtractive manufacturing, which is considered as more traditional manufacturing, but manufacturing parts additively, which can have benefits in creating parts that are stronger, lower cost, things of that nature. We do a lot of work with aerospace, but also industries such as medical devices, consumer products, naval and defense, really across the spectrum, all manufacturing industries can be impacted by this. I think that some of the benefits are that companies can become more efficient in their workflow. There are a lot of areas where we try to help companies identify where there might be standstills or areas where they could, save time, and ultimately that will help the company to save money as well. And it also opens up new doors for the types of products and the types of parts that people can manufacture that previously wouldn't have been possible with technology that we had in the past. So one of our focus areas is actually generative design. And generative design really represents a huge fundamental change in the way that we're able to design parts. So previously we were limited by subtractive and traditional manufacturing methods, but generative design allows us to design for function. So rather than being limited by that technology, we have more doors open and we can create shapes that are organic in nature. We can create parts that are lighter, stronger, lower cost. We can consolidate assemblies of multiple parts into fewer number of parts. Which ultimately helps to benefit the company and their efficiencies. And we're in a sense designing for additive in that way. And then sort of after that, once you've been able to manufacture the part, there's also inspection, which is a huge part of the industry. And with technologies such as in the areas of non-contact inspection, such as CT scanning, we're able to inspect these parts, detecting voids or other inconsistencies in the part, ultimately resulting in a high quality part. With non-contact inspection, we can inspect parts that have complex geometries, things that have very small features, so things that might be more difficult to inspect with traditional contact methods. And also if there are industries that don't want us to touch the parts, non-contact inspection is also an added value there. Yeah, and it's really crucial, especially in the aerospace industry, that the parts are manufactured to a high quality and a certain precision. So I've been at CCAT for a little over 3 years. My background is in mechanical engineering, and what's unique about CCAT is that we're working with all sorts of different populations. So students all the way down at the middle school level, introducing them to manufacturing and the types of careers that are available. We work with high school students, job seekers, all the way up to incumbent workers and providing training for employers as well on all the different types of technology that are available to them. Yes, so it's very rewarding working with young students and seeing them become excited about programming a robot or creating something in CAD. And for me, it's really about building their own confidence and showing them that this is something that's accessible to them. They can learn it too, and if it's something that they enjoy, they can have a really successful career in the industry, because there are so many opportunities right now for students in Connecticut, and there is a huge need and a huge skills gap that companies are going to need to fill over the next 10, 20 years, and there are just not enough skilled workers to fill these positions. Which is why awareness and building skills for students at a young age is so important. There's a huge shift towards Industry 4.0 right now, and that encompasses a number of different technologies, including additive manufacturing, simulation, big data and analytics, cloud computing, cybersecurity. All of these different technologies, the move towards smart manufacturing is where the industry is moving, and where Connecticut is moving as well.
So my primary responsibilities here are anything related to advanced design, automation, and metrology. Technology that we can use to help companies redesign parts that are optimized. Automation systems we bring to small and medium companies to help them automate a lot of their tasks that they're doing, to streamline processes. Ultimately, we want them to build better parts faster and at a lower cost. And then on metrology, we use advanced non-contact inspection systems that can both see part surfaces and also through parts. We'll take a look at a part and we'll see the processes that are used to produce that part. We can take that part, whether it's a single part or it's a multi-component assembly, and we can consolidate it into a single part and actually change the shape or optimize the shape such that it becomes a stronger part to produce, and we can target a specific manufacturing technology to produce that part. Typically, we'll aim for additive. When you're designing a part, you're in the back of your mind, you always have, how am I going to produce it? When you're talking about, using technologies like additive or using technologies like, 5-axis CNC machining, or in some cases robotic machining, and you can remove a lot of those constraints and focus more on the functional requirements of the part. So now the shape of the part can be optimized because I'm not worried about how to produce it. Additive technology essentially removes a lot of those constraints. It is a paradigm shift where traditional design, an engineer would sit down at a computer and you would essentially tell the computer what to do. With the advent of artificial intelligence, machine learning, we can actually we can use the computer as an aid or as a support to help us design the part. And all we have to do is tell the system, where are my loads, and it'll actually come up with designs for you that look like they would have been grown in nature. And this is what these kinds of AI-based systems do, is they completely optimize the shape based on the functional requirements of the part. And then the other neat thing is that along with that, we have technologies that are advancing in inspection. Non-contact inspection is one of those technologies where you can capture any shape almost instantly and be able to measure it. So it doesn't matter how complex it is, you can capture it, you can measure it, you can capture external as well as internal defects on the part, and you can really get down to seeing how that part was made, what are all the different flaws and issues with that part, and then even make design iterations based on that. The most used item is structural light scanning. That technology is you can consider it just like a camera, where when you take a picture you get color information, you capture the scene. With 3D scanning, you're capturing geometry, 3D geometry as well as the color information. We're getting, down to, if you were to kind of help visualize it, like fingerprint detail, we can get down to very high resolution. We have done medical parts, we've looked at automotive parts, we've looked at naval maritime industry parts, and but mostly it's aerospace parts, and we're looking to get down to very high accuracies when we're doing that, as you can imagine. The other things that we look at here at CCAT are technologies related to Industry 4.0. And in order to do that, we're adding sensors to machines, we're adding automation systems that can handle, for example, part loading into machines or post-processing steps such as deburring and even assembly. This whole area of adding either sensors on the machine or reading information that the machine already stores internally, tapping that information out and streaming it to a central processing unit, like a computer unit or software, that takes that information and gives you something useful back. What machine learning will do is it'll take the data off the machine either through the sensors that you put on it, or if the machine can communicate itself, and output data. All that data can be looked at over time, look at trends, and then the system actually gives you suggestions. Should I change the speeds at which something's happening? Should I change the feed rate of something? It's things that you wouldn't normally think of, but because you have this background system learning how the machine functions, it's taking data from all different aspects of the whole process, saving tool life, or extending tool life, reducing machining costs, and again, ultimately, this all goes towards producing better parts faster, cheaper.
A couple different areas that I've focused on. One is we're bringing in some systems for 3D printing with robotics, bringing in the equipment, getting it set up, really kind of figuring out how it works. There's a lot of advantages to printing with robots. Another area that I'm working in is helping companies in the area figure out how and where to implement robots and automation technologies in their workforce. Most people, when they think about robotics, they're picturing the Ford assembly lines from 20, 30 years ago. And robots have moved a long way since then. They can do a lot more than they could before. So part of my job is to help educate and to really try to help them figure out, does it make sense for me to bring in a robot? What kind of an ROI can I get off of it? Where can I put it? And what kind of jobs can I realistically expect it to do? I also try to work with the robot OEMs themselves. I try to get in contact with them and figure out what do you have, what's new, what's coming out, so that they can get a good feel of where the technology is headed. So if you've got a steady product that flows through a shop, a manufacturing facility at a regular basis, those are easy to automate. That's where it's easiest to get your return. I've seen everything from, actually I had a guy talk to me about automating meat packing plants. That's one end of the spectrum. The other end of the spectrum is unloading a machine, opening the door, pulling a part out, stacking it in a crate. Again, traditionally, robotics have been set up by safety fence. Where the robot works is where the robot works, and humans don't enter. There's been a lot more of a focus lately on we need to have humans be able to work side by side with robots safely. Robots are not very good at improvising, and humans are. So to be able to have the two working together, so when something comes along that the robot can't foresee, it's not programmed for, the human can do it. You know, the simple stuff, pulling something out, putting in a box all day long, you know, pushing a button all the time. All of those are things that people really don't want to do. Robots do it very well and they don't complain about it. Well, robotics here, we use them for a variety of things, and we're working on a lot more applications. The biggest one at the moment is we use it for inspection. We use them to maneuver cameras around in automated inspection systems to help them. The other part that we're doing with them is we're trying to put together demonstrations for our customers, for the businesses in the area, to really show, again, this is what robots can do. One of our big purchases that we're hoping to bring in here very shortly is a robotic printer. That's one system we're doing. We're looking at building another metal additive system, which will more than likely be a robotic system as well. And I'm working with selecting the right robot for our application, working with the integrators and the OEMs of the robot to figure out who makes the best system for us. We're trying to expand our offerings. Automation is a big part of what's coming in the future. You know, can you help us out to showcase both your products for our customers, but also we want to be able to help you reach more customers in this local area. So part of the expansion is to open up room for that, to be able to bring in some of the newer technologies, whether it's collaborative robots, whether 3D printing systems, metal printing systems. All of what we do here really goes hand in hand with that. And a lot of it is really to increase the throughput of companies without having to increase the amount of manpower, labor that is needed. My recommendation to a lot of companies is, hey, let's look at your process. Can we automate the standard run-of-the-mill stuff so it can run lights out, second and third shift, so then you can move your people off of second and third shift and put them on something that's more friendly, where they're able to work during the day on the stuff that's you need direct human intervention for. There's not a good enough skilled workforce to enable that increase in throughput, increase in capacity without automation, robotics, and other digital technologies. But what it lets us do is it gives us a platform that we can try multiple technologies quickly to help select which technology is the best for the individual person or company that comes to us looking for solutions. The robotic solution just gives us the flexibility to show the maximum return on our investment and to show the maximum amount of technology in a way that is scalable and easy to transfer.
name is Henry Babiak. My title is a manufacturing applications engineer. So what I do is basically operate the machine that's behind me. So what the machine is a 3D printing machine combined with a subtractive machine. So what we can do is use metal powders to print a part and also high precision machine them. The term subtractive is kind of new because now there's 3D printing, so it's an additive technology. So the subtractive is now a term that was always the way we manufactured, which is using regular machining tools to machine parts. So this machine has also a capability of turning and 5-axis milling. So in the industry of aerospace, it's a highly utilized, more efficient machine because it has 2-in-1. So technically this machine is a 3-in-1. You have the 3D printing, turning, and milling. So some of the projects that I have been on are specific to the aerospace industry. More specific would be space industry. So there's a lot that has been in practice in the printing for the space industry. I mean, we all hear SpaceX and Blue Origin and the others. They're highly utilizing the technology right now. So here we've been more involved with projects that are lower level research projects in the industry, specifically for NASA and other clients. So it benefits in the fact that we can do it all in one machine rather than have it in multiple other machines, and so the project is more based as start to finish on one machine, one platform, and that way the industry looks at that as a better practice because of efficiency levels. So that this machine is one of, I guess you could say, top choice in the industry for that reason. So this one, we have it at CCAT now for around 3 years. So I can add or remove material basically on the fly without removing the part, making things more unstable, things like that. It stays in the machine while I remove or add as many times as I want, back and forth, whatever needs to be. So if there's something that didn't come out right, or if I need to repair a part, I just machine it off and start printing without multiple setups or other issues. So the efficiency, the time savings, the amount of material being used. Technically, when you're printing metal, you're only printing in the area that needs to be. You're not machining away that much. So it's in the industry we call it near net shape, where you're as close as to the final product as possible, and then the final machining is more of just finishing rather than roughing a ton of material away.
I am working in this AFP lab, which stands for Automated Fiber Placement, and that is a process, an advanced technology that applies carbon fiber to tool to make parts. So you apply carbon fiber in layers to build up a part, and we do that here as a special operation and a very special technology. So what we do is we have a process here that we can take from carbon fiber, which is almost, you can think of it like a fabric. It's a fiber that's embedded in a epoxy matrix, and so from zero you have in essence just these fiber strands, if you will. And then from there you would go through this process, and then you'll end up with a physical part. And these parts are used all over in more advanced technologies: Formula One race cars, MotoGP motorcycles, off-road racing trucks. Aerospace is obviously a huge one because of its mass. It's very light and very, very strong. The magic of carbon fiber is that it's tunable depending on what orientation you apply it in. Carbon fiber manufacturing is a very labor-intensive process. There's a lot of hand cutting, especially when we get into what we think of as 3D contours. Not just flat pieces that you're building up these layers on. It's think about a boat hull or various other shapes that like a car frame or a wing on a car. Those shapes are very difficult to lay a flat piece of material on. And so this machine allows us to, via the robot, allows us to follow a trajectory that keeps the carbon fiber orientation such that the robot will follow a 3D contour and the carbon is laid on there and does not bind up or wrinkle or fold. So it's able to really precisely place these, what we call toes. This system has a laser inspection. So what happens is the robot will swing it over to a laser system that projects and scans the laminate and finds where there might be gaps between those 2 1/4-inch toes, or where they may have overlapped a little bit. And there'll be, depending on what part you're making, there will be requirements on how much overlap or how much gap you can have, or how much variation in fiber angle. This whole lab and facility is an R&D facility, so we don't do production parts here. So we are, in essence, developing the process that would be needed to make a production part, and this system could be scaled in a factory kind of setting. So we do things where we'll take a concept from a designer, the 3D program will be written, and then we will produce it on this machine, and there'll be problems found along the way. And that's where we have the beauty of having a robotic system, that we can eliminate a lot of iterations of, okay, well, we tried this and I made these slits in the wrong place because it has to contour this surface. Now we need to go back and do something else, and we have a lot of waste. With our system, we're able to reduce the number of iterations required, and also establish these processes and requirements that would be needed that you might not be able to get otherwise. And so this technology allows a lot of repeatability. It's very accurate, and so your end product that's a development product can be produced quicker and more accurately and be a better part initially than you would have to otherwise. For example, in this lab, while the machine was being what's called an acceptance test, we still made a part that ultimately was going to be made on the robot, but we did it by hand. And it must have taken us 4 times as long to do it by hand as it would have on the AFP robot. So we know there's significant savings, and the technology that's in here to be able to allow you to make more complicated, more complex geometry, it's far superior than anything you could do with your hand layups. And on top of that, with the way the inspection system works, you get feedback immediately on whether you have successfully laid down those fibers or those toes, and can solve that or remedy that right at the time. So AFP and something else called ATL, automated tape laying. So a lot of folks in the world have heard of the Dreamliner, the Boeing 787. Its fuselage, the big cylinder that makes the fuselage, is done in a similar process, where there's much wider carbon fiber tapes that are placed by a robotic machine, and the fuselage is in essence wrapped, if you can think of it in that way. If you think of what it is, though, it's a relatively continuous cylinder. So that surface is pretty regular that you're putting carbon fiber on. The magic of AFP is that as you get a more complicated, more kind of organic 3D shape that the robot has to follow, having smaller toe widths allows that nose of the robot, or the head, to lay those down and follow these 3-dimensional contours a lot better. You couldn't do that with a wider piece, which is, so when we use AFP, you're basically saying, okay, we can follow much more severe contours than you could in a conventional flat layout.
Thank you for being with us. It's a tremendous honor to work with such talented people, and we welcome the opportunity to work with you. To learn more, visit our website at ccat.us.